Yeah.
Our next speaker is Cameron Musco. His title is Randomized Block Iterative Methods for Singular Value Decomposition.
Okay, so I'm talking about randomized iterative methods for SVD or partial SVD. This is joint work with Chris Musco, who's my brother. So sort of the outline is that recently in the machine learning and data science communities, randomized block power method has become super popular and super widely implemented. By randomized here, I just mean literally starting with random start vectors. And block power method is just plain vanilla power method simultaneous iteration. The reason for its popularity, I think, is mostly because it's a super simple to implement algorithm. And also recently, people have shown some strong convergence guarantees that apply specifically to low rank approximation and dimensionality reduction problems that people in the ML community really care about. And sort of the strength of these guarantees that they're generally independent of your matrix spectrum. So for typical eigenvalue problems, you're going to expect your convergence rates to depend on your spectrum in some way, like on your eigenvalue gaps. These sorts of guarantees are independent of those gaps, so apply sort of to generic matrices with no assumptions. So in this work, we basically extend these guarantees to block KRYLOV methods, which as expected outperform the power method, both for the theoretical bounds we can get and also in practice. And so we hope that this will lead to the adoption of these block KRYLOV methods for these very large scale problems that people in ML are solving. In the process, we introduced some new analysis techniques based on viewing these KRYLOV methods as sort of denoising procedures for random sketching methods. So I'll talk about those a little bit. Okay, so everybody understands the SVD very well. In machine learning, it's a super important primitive, and it's typically used for dimensionality reduction. And specifically, it's used for low-rank approximation and principal component analysis. So we know that the singular vectors of the matrix are just defined as basically the eigenvectors of A transpose A or else AA transpose. And this means that they're sort of the directions of largest variance within your matrix. So what this gives you is that once you have your singular vectors, you can immediately read off optimal low-rank approximations of your matrix. So if I truncate off all but the top k singular values, I get this from matrix AK, which is the best rank k approximation for my matrix A. And this is best in the sense that if I look at the Frobenius norm error A minus AK, this minimizes the Frobenius norm error for all rank k matrices. And this holds for any unitarily invariant norms, so like the spectral norm is another norm that people really care about. So with the SVD, we can read off optimal low-rank approximation. You all probably know this, but just to mention, AK, it can also just be viewed as projecting the matrix onto the span of its top k eigenvector or singular vectors. And you could project on the right side. I'm always going to use column singular vectors for the purposes of this talk. Okay, so if we're using the SVD in order to do optimal low-rank approximation and principal component analysis, it makes sense to define our error metrics in terms of these goals. So one thing we can do is we can ask for an approximate span U tilde k that basically gives you near optimal Frobenius norm reconstruction. So if I project my matrix A to U tilde k, it's going to be within 1 plus or minus epsilon to the optimal Frobenius norm error for the distance from A to any rank k matrix. Now this is useful in many contexts, but it can also be super weak. So recall that the Frobenius norm is equal to the sum of the squared singular values of a matrix. If you look at this optimal Frobenius norm error, A minus AK Frobenius norm, this is basically, AK contains the top singular values of the matrix, right? So when you subtract it off, you're left with all the remaining tail singular values. So this Frobenius norm is equal to the sum of the small singular values of your matrix. Now, traditionally, you think of this as being relatively small. So almost all data matrices display like relatively strong spectral decay. So the large singular values are significantly smaller than the small ones. But if you have a very high dimensional problem and you sort of don't have super strong decay, this sum can end up being quite large. So unless you set epsilon to be very small, this guarantees in like many cases is meaningless. So if you start playing around for many data sets, unless you're setting epsilon to be very small, you can return all sorts of answers for U tilde k, and you can get this sort of approximation. Basically, you're not able to do great Frobenius norm approximation anyways, even though you have a somewhat low rank matrix. Okay, so to strengthen this guarantee, a sort of easy thing to do is you can look at your spectral norm error. So the spectral norm of A minus its best rank k approximation is just equal to its k plus first singular value. So this doesn't depend on the size of the matrice's tail, and in general is going to be a lot tighter bound. In order to achieve this sort of bound, U tilde k is really going to have to align with any large eigendirections in your matrix. It's really going to have to project off any directions of major variance, and therefore it's going to be a better set of principal components for your data, basically. A final way that you can measure error is that note that in these first two metrics, we're only looking at the projection onto util decay. It doesn't actually matter the actual approximate singular vectors we're outputting. It only matters what the span is. So if we want these approximate singular vectors to actually be good principal components for the data, what we can do is we can ask that the dot product of u tilde I over our matrix is nearly as good as the dot product of the true singular value vector over the matrix. And that's just the squared singular value right there. So that's the strongest guarantee that we'll look at. And we're basically going to show that these KRYLOV methods give all three of these guarantees simultaneously. I'll just mention that none of these is actually strictly stronger than the rest. Technically, there's cases when one is stronger than the other. Even Frobenius norm can be stronger than the other two. But for typical matrices, this is sort of the order of how strong that they are, how hard they are to achieve. Okay, so if you're okay with Frobenius norm approximation, there's various options. You can use like a strong rank Levy QR algorithm, and you can get a util decay that gives within polynomial the optimal Frobenius norm error. This seems really weak, but if you have something that's basically like numerically low rank, this is going to give you something useful. So basically, if A minus AK is extraordinarily small. You can use randomized methods like sparse subspace embeddings, or also Johnson-Lindenstrauss projections, random sketching, or some other names for these methods, where you basically just randomly multiply by your matrix by some random Gaussians and take the SVD of that and return that. And this allows you to get 1 plus epsilon approximation in this norm in super fast running time. So basically order the number of non-zeros in your matrix plus some lower order terms. But again, if the Frobenius norm approximation metric is weak, this can be like not very useful. Okay, so if we want stronger guarantees, really the only option is to turn to iterative methods. And what I'm going to talk about here specifically are the power method and KRYLOV methods, or block LANCZOS methods. So everybody knows the traditional power method. I start with some initial vector. In our case, it's always going to be a random vector. That's actually where the title randomized comes from. It's just that you start with a random vector. You multiply it by your matrix in each iteration, and you normalize it, and it will converge to your top eigenvector. The block power method, or simultaneous iteration, subspace iteration, you just have a block of k vectors where k is the target rank that you're going for. So if I'm trying to get a rank k approximation, I use a block of k vectors. In each iteration, I multiply by my matrix A, and I orthonormalize to keep my condition number reasonable. And at the end, basically, the span of my block is going to converge to the span of my top subspace of my matrix. Okay, so we can bound the runtime of block power method. Basically, the cost per iteration is you have to do k matrix vector multiplies, so it's the number of non-zeros in your matrix times k, and then times the number of iterations. If you start with a random vector, your initial error is something like polynomial in your dimension. You can prove that. And so you have log d over epsilon when you have linear convergence to get down to epsilon error. And then your convergence rate always depends on this gap parameter, which is basically how much larger your kth singular value is than your k plus first singular value. So this is just traditional like power method convergence rate. But unfortunately, the gap factor is often the dominant term in this bound for many data sets. So if you look at super high dimensional data sets, like this is an adjacency matrix of a large social network graph, it has initially strong spectral decay, and it's something you might want to actually do some principal component analysis on and find these large principal components at the beginning of the spectrum. But after the initial decay, the spectrum flattens out super quickly. And if you look at, for example, here I just looked at the median gap value for the top k singular values, and it was something really small, like 1 out of 500. And if I looked at the minimum gap value, it was like super small, like 1 out of 25,000. So if you actually plug this into the bound you're getting for your runtime, it's like a huge cost factor. These gaps are very small, especially if you're not going for very small epsilons, which people in machine learning and data analysis aren't going for very small epsilons. But you can get around this. Basically, recent work shows that if you want this sort of guarantee, like this low rank approximation guarantee, a near optimal low rank approximation, you can replace your gap term with your epsilon parameter. So you can converge in basically log d over epsilon iterations. So as long as epsilon is bigger than your gap, this is going to beat these classical bounds. I mean, it's the same algorithm, it's just a different bound. And this is often the case in practice. So often epsilon is going to be larger, especially in very high dimensional problems where you don't have very tight tolerances. This is like going to often be the case. This was first proven by Rockland, Sam, and Tigert, and then it was really popularized in the machine learning community by Halko, Martinson, and Trop. And then there's been a lot of subsequent work. And it's become very popular. So basically, this block power method using like a few iterations in a randomized start vectors is implemented in all sorts of large-scale learning libraries. But this kind of contradicts the fact that Usually we think of KRYLOV and LANCZOS methods as being sort of stronger than power method and that they can offer better convergence rates. Basically, if you look at sort of this bound that I gave for the power method and you want to look at, yeah.
Just so I understand, randomized power methods, you're just going to see the iteration?
Yeah, it's literally just power method. Really, the only reason I'm calling it randomized power method is this is sort of what people call it in the literature that's been talking about it. But it's just power, like it's a simultaneous iteration. That's it.
Okay, so what did American Alpha Computer been doing for 34 years?
Yeah.
Got it in the name.
Is now becoming popular. Yes. Yeah.
What do they call? What do they refer to as power? If they refer to
The block has one column.
I mean, they don't. I don't know. They just call it this randomized power method, right? They don't talk about like. This is just what they call in these papers.
Oh.
And this is what they're using. It is the power method. Like, there's no difference. It's what people have known about forever, right?
It's randomizing first by multiplying by.
Yeah, I mean, I can explain in more detail. So the reason they think about it as being randomized is they sort of view it as so you can also just apply like one iteration power method where you literally multiply by a random matrix, take the SVD of this and output this as your result. So this feels more like a randomized method essentially because your output is random basically. You're not getting like actual convergence, right? So that's why I think that term started being used, but it really is just the power method with different iteration counts. Yeah. Okay, so if you look at basically this gap-dependent bound that I was showing, and you have a similar bound for KRYLOV methods, you just get some sort of like standard acceleration where you can get like a square root dependence on your gap basically. And so recent work has shown these 1 over epsilon bounds for the power method that have no dependency on gap, but there was nothing for KRYLOV methods. So what we're basically doing is just showing that you can get the same acceleration when you have these gap independent results. So you can get your epsilon to go to a square root of epsilon, and you don't have this gap dependency, so it sort of applies generically to spectrums. Okay, so that's our main result basically. It's a runtime bound that's totally independent of the spectrum of A. It beats power method significantly for small epsilon, and obviously in practice for various other reasons. And then it improves the classical bounds whenever your epsilon is bigger than your gap. So it's not really, I'll explain what this algorithm is. Basically, we're going to be applying block LANCZOS. It's not a new algorithm, it's just a new analysis that's giving a tighter bound. Basically, it's giving a tighter bound when these are the guarantees you care about. So basically the key insight is to ask, well, okay, where does gap dependence come from? So in all the analysis of power method or LANCZOS methods, what you usually see is you're arguing about convergence between your approximate singular vectors and your true singular vectors. And you're measuring this with something like the 2 norm between these 2 vectors. And then you can generalize this. You might be looking at the subspace angle between your true top subspace and your approximate top subspace. But like morally speaking, these are sort of the same thing, right? And we know that this is a great potential function, right? It's easy to work with. You can show that it's improving in each iteration of power iteration. And you can immediately use it to prove the sort of low rank approximation or principal component analysis guarantees that people in machine learning care about. But it inherently requires iteration count that depends on the singular value gaps. So if you're actually asking for this sort of convergence, you inherently have to depend on the singular value gaps in your matrix. And probably most of you have very good intuition for why that is. It's basically because if you think about power method, right? If I'm powering up and my top eigenvalue is only slightly larger than my second eigenvalue, I'm only going to converge very slowly to that top eigenvector. But the point is that convergence becomes less necessary precisely when it's difficult to achieve, right? So if I have a small gap, if I have this 1.01 eigenvalue and a 1 eigenvalue, I'm going to get really slow convergence. This isn't that small of a gap, but I'm going to get rather slow convergence. But in this case, for low rank approximation or for principal component analysis, it really doesn't matter if I return the second eigenvector or the third eigenvector or some combination of those 2. So basically, while minimizing this sort of traditional error guarantee is sufficient, it's totally not necessary for low rank approximation or principal component analysis. So that's the intuition for why you can remove the gap dependence. I'm going to talk a little bit about the proof methods we use, but really the intuition is what matters. The way that we prove this is sort of just, we view iterative methods as denoising procedures for random sketching methods. So basically, if I take a matrix A, which is rank K, the most basic random sketching method I can use is I choose a random Gaussian matrix with k columns. Say I'm in infinite precision. If I multiply my matrix by this Gaussian matrix, the span of this is equal to my original span, right? If I set u tilde k to that span, I then project to u tilde k. I'm just projecting to the span of A, so I exactly recover my matrix. So I've basically done an optimal low rank approximate matrix when my matrix was rank k. If A is not rank k, then I'm obviously going to have some error due to basically the tail A minus AK. So specifically, I can show that this Frobenius norm error is smaller than some polynomial factor of the optimal. This basically gives an error bound for a single power method iteration. And this sort of algorithm is actually used a lot in the machine learning community. It's sort of why maybe these methods were sort of called randomized methods originally, because it's basically a single power iteration, but it's quite a randomized algorithm because you have no convergence whatsoever. It's very weak unless your tail is very small. So the question is, how can we make this tail noise small? And what we're going to do is we're going to think about applying this. I mean, this is just power method, but we're going to think about just applying the sketching method to A raised to the qth power. So this is exactly what power method does, ignoring orthogonalization just for like exposition, right? Basically, power method is returning the span of A to the q times some Gaussian matrix. So you can view this as applying a random sketching method to the matrix A to the q. A to the q just has all of its singular values raised to the qth power. So when you plot the spectrum of A to the q compared to A, and you scale so they have the same top one, basically all the small singular values of A to the q obviously get squashed by the powering. So this tail size for A to the q, this sort of Frobenius norm error on A to the q to its low rank approximation is very small. I'm going to skip sort of the details, but it makes sense why you'd have to set it to the iteration count to 1 over epsilon to kill off any very small singular values. But in the end, basically, even with this very coarse guarantee we get from the random sketching method, we know that u tilde k basically must align with any significantly large eigenvectors of A to the q. These are the same as the singular vectors of A, so then we can basically show that this is a good approximation. I'm skipping tons of details. I'm just sort of explaining the high-level way that we go about these proofs, because it's not really a very standard way of doing proofs for power method. You then take this very small Frobenius norm guarantee that we get, and you can convert it to the spectral norm and these PCA guarantees. I'm going to skip the way you do acceleration. It's sort of obvious how you do acceleration, right? You know that there's a better polynomial for than A to the q. You can use a Chebyshev polynomial. So what you do is, instead you can't explicitly compute this Chebyshev polynomial matrix, so you just construct a KRYLOV subspace, and you return the best answer in the KRYLOV subspace. But what I want to just mention quickly is that this is not that easy of a question to answer. What is the best answer in the KRYLOV subspace? So in traditional analysis, you use like the Rayleigh-Ritz procedure, right? You project your matrix to your subspace, and then you take the top k eigenvectors. There are no proofs of that this really works when you don't have convergence. But what you can do, and this is actually our algorithm. We compute the KRYLOV subspace, and we do the Rayleigh-Ritz procedure. But it's not clear that this works when you don't have convergence. And actually, what you can do, I'm just going fast because I'm about to run out of time. You know that the Rayleigh-Ritz procedure is optimal for Frobenius norm error. It gives you the best Frobenius norm low rank approximation to your matrix within your KRYLOV subspace. It's easy to show that it's suboptimal for spectral norm and PCA error. But because our proofs went through this Frobenius norm approximation guarantees, we immediately are able to show that our Frobenius norm error is good and then convert it to our other error bounds. So the takeaway from this is basically, it's sort of a different way of looking at the Rayleigh-Ritz method when you don't have convergence. There might be other ways to prove this, but this was sort of why this proof technique ended up working out well for us. Let me just do a quick conclusion. These are very well-known algorithms that we're looking at. We're basically looking at like large block LANCZOS and power method. But they've recently become very popular in the machine learning data science communities. And the point is that's because they're super simple and they have super simple guarantees. And so by providing these sorts of guarantees and providing these algorithms to that community, it can really affect what they do in practice. And then also I feel like by looking at these algorithms from this perspective of that community, it can give sort of new understandings of different ways you can analyze this algorithm, which might be of interest to this community. Thank you.
Questions? Comments?
Okay, so how can you practically measure the accuracy of this matrix?
You mean because you can't measure how close you are to the actual optimal spectral norm error?
Yes.
Well, so at least for like the PCA, error, you'll get some sort of sense of convergence because you'll know that basically you're not getting, you can test for convergence to at least getting near the singular value you're looking for. I'm not totally sure how you can do a good stopping criterion for the spectrum or error. I'd have to think about it. Mhm.
In practice, how do you choose the number of rank factors? G.
Okay, so if you want gap independent guarantees, you have to choose it to at least be the size of the rank you're going for, so whatever the rank you want to project down to. I sort of skipped this, but in practice what people do is they actually choose it to be like the size of your block to be something like twice the rank that you're going for. And this can work super well in practice because then your gap dependency becomes on the singular value gap between your k at singular value and your 2k at singular value, which can be really big. So actually, in machine learning libraries, you'll see these really weird implementations of power method where they basically choose a block size that's like 5 times the rank that they're going for, and then they perform like 2 iterations of power method, or like 3 iterations of power method. So it almost doesn't even look like power method because it's so many few iterations, but it's because you can get super fast convergence when you have really large block size.
That's the trade-off, right? You gotta.
Yeah, that's a
storage requirements, right?
yeah. So that's a trade-off, but for them, k is usually considered extremely small. So it's not a huge trade-off like, to double your block size.
But your k gives you final approximation
Mhm.
in Frobenius norm. So if you want better lower approximation, you have to increase k. Right? And then, so
You can increase the number of iterations or increase k, I guess. Or, wait, sorry, what are you asking?
the quality of the final product that
Yeah.
you have, as you increase k, you get
Yeah.
better lower approximation.
Yeah,
Right?
right.
So that's you're dealing with the convergence to the low rank approximation you've picked, and also should I choose a bigger rank?
Oh, no, I'm not talking about, I'm just talking about using a larger block, but you still output a k-dimensional substance.
Excuse me, time's getting really short. We better start setting it up for the next speaker.